Okay, so continuing with chapter 4, we were talking about the sun angle and how it varies with latitude and on particular and so far we've only talked about it on a special day of the year, which
The
is the
the slides disappeared.
okay.
Not on
It's
the.
just the summer solstice. Thank you. Let's figure out why.
Hey, there you go. Thank you.
Yeah, of course. And so see if they will stay visible this time. All right, there we go. So we had seen this formula right here, which was a formula that described the sun's altitude. Remember, altitude is, like the picture shows, the angle above the horizon at the summer solstice. And the formula let us find that altitude based off of latitude. So the variable was latitude, and axial tilt was always a fixed value of 23.5 degrees. So as long as you're only concerned with this particular day, the day, coming up in 4 days for us, June 21st, although sometimes it's on the 20th, just to, they'll announce, when it's on the 20th. And suppose it might have sometime been on the 22nd because, there's always a little bit of variation because of some of the rounding with the days. Basically, there's not exactly 365 days in a year. There's not even exactly 365.25 days in a year, which actually is one of the last slides in this very lecture. But anyway, there's somewhere around June 21st. If it's that date, use this formula. This is for the northern hemisphere. I I will in a few minutes tell you how to use it for this the same formula for the southern hemisphere. But for now, think of it as just applying to the northern hemisphere. All right. So, and the takeaway is that the sun is pretty high overhead, um, at a particular latitude. And this is, decently high. This would be, really would feel like a hot summer day. But of course, if you're really far north, then even at the summer solstice, the sunlight is not very direct. Okay. So visualizing the sun angle in winter. Okay, so far we've been talking about it in summer. We saw a very similar figure that showed the northern hemisphere when the North Pole was tilted towards the incoming sunlight, but now we're tilted away because this is the northern winter. This would be the December solstice. Okay, either around or on. And it's best to think like we're just talking about special days. So we're just talking about the December solstice. Okay. So when you look at the sunlight and its relationship to the vertical direction, okay, we have this 67 degrees, and the 67 is coming from the axial tilt. And what they did is they took the axial tilt and they made it 23, at least for this approximation. And it's it's fair to say that the sides here do jump back and forth between sometimes using 23 degrees for the axial tilt, um, and then sometimes rounding it up to 24. With the recent quiz, those of you that have taken it know. Those of you who haven't, this is a hint that I just use a 23.5, so you would just include that decimal place. And so this just comes from 90 minus 23 degrees. Okay, that's where the 67 comes from. Okay, and that dashed line, what does it point to? It points to the zenith. So the zenith of the observer. Okay, at whatever latitude that observer is at. Okay, so let's take a look at the winter solstice. As we can see, the sunlight is not as direct. What's kind of fun about these pictures is that the light does noticeably seem lower here. Notice the shadows and the overall look of the light. It's less directly overhead. So this would be, midday in the winter as opposed to midday in the summer. And it's noticeably different light, although the dogs are still taking advantage of whatever sunlight there is, but it would be less intense. So in this case, the altitude of the sun at the winter solstice, so this is as high as the sun will get on that day, is 23 degrees. So you think of the sun as peaking out at 23 degrees. So, if you can visualize the path of the sun, it would be rising in the east and setting in the west. No change there. And not exactly due east or due west, but pretty close. And then it would take an arc across the sky, but never really rising that high into the sky. So it would take an arc, staying fairly low at this particular latitude, and never getting higher than an altitude above the horizon of 23 degrees. And that arc for everyone in the northern hemisphere would be towards the south. So you would see, so that peak altitude, say at noon, would be in the direction of the south. Whereas if we were talking about what winter would look like and the sun not rising very high above the horizon in the southern hemisphere, well, then the arc is towards the north. So that's a difference between the two hemispheres. But for us, we always think of, the south facing direction as always getting more light, and that's a unique feature of being in the northern hemisphere. And the formula for the peak altitude of the sun on this shortest day and least sunny day is the following, right down here. And it looks pretty similar, right? The difference is that we are taking the axial tilt and we're subtracting it instead of adding it. So we got 90 degrees minus latitude minus axial tilt in order to get the 23 degrees. Okay? So could we use this formula to remind us of what the latitude these dogs are at? Is you might remember from a few slides back where this northern hemisphere location is, but if so, don't say it, but think about how you would use this formula. But instead of just using it to find the 23 degrees, using it to find the latitude. So I'll write it out and I'll put in, let's do, sure, 23. And I'll include the axial tilt as 23.5, and we'll find out what latitude that gives us, which might be zero point 0.5 different from what it was on the slide. These are the slides that we didn't see today, that what we would have seen yesterday. And once I write out the formula, I'll check chat, and I want to ask you to find it. So what you should be doing right now is just thinking about, doing the math and solving for latitude. I'm putting in the value of axial tilt. So I've only left one variable. This is essentially your x right there, your latitude. So what is that value? I'll do it as well. And you can just tell me with your microphone too if you want. Okay. Are you sure it's negative? Check your math. This is the response to Maxwell's answer you put into chat. You shouldn't get negative 43.5 degrees. for the latitude. Because if I would imagine adding the latitude to both sides. So I'm going to put, oh yeah, yep. You know what's the most common mistake to make in an algebra equation like this? The sign, getting the negative wrong. So it's like really, really easy to do. So what I did is I just added latitude to both sides, so it became positive. And then I'm also going to have simultaneously subtracted the altitude, the given altitude at the winter solstice from both sides. And then the axial tilt value as just along for the ride. So I've just left it on the right-hand side of the equation unchanged. And when I do that, and I have my 90 minus 23.5 minus 23, I get 43.5. Does that make sense, everybody? Any questions on that?
So I had a question. What I had did was I took 90 degrees minus the latitude, and to find a latitude, I used the other slide where it said latitude was 43. So I did 90 minus 43 minus 23.5 for the axial tilt.
I
And I
mean,
don't,
that would be a way to like confirm. The only difference about your method is you're taking the known latitude and making sure it works, right? Whereas I was saying, okay, well, what if I had forgotten that other slide? What if it had disappeared? I didn't know it, and I wanted to remind myself or find that value anew. You see, same math, same idea, but just slightly different set of goals or different, guidelines.
so where did you get the point 0.5 from after the
Um,
43?
I got it because I didn't go back to the other slide. I said, okay, well, what if I'd forgotten about because they and as I mentioned, the slides here tend to round and they leave off the point 0.5 for the axial tilt. Okay. And
Okay.
yeah, so that's so if you don't, if I don't solve or if I don't go and refer to the other slide that gave the latitude of where these dogs are located, if instead I just solve for it, then I get this value by just plugging in 90 minus 23 minus 23.5.
So I did it wrong.
Not significantly, no. What you did is very, very close. I was just trying to explain the small, subtle difference between what you did and what I did.
So you solve for latitude by
By
doing
re
these.
Yeah, by rearranging the equation.
Okay,
Yep. And yeah, exactly. Treating it like a math equation.
gotcha.
Cool. All right. Uh, let's carry on. Okay, so now here's another equation. And what this is going to focus on is why having the sun at lower altitudes makes such a big difference for the heat that the sunlight delivers. Uh, I'll just quickly point out that heat has an official definition in physics and astronomy. It is energy. It's measured in the same units as energy, which are joules. And if there's less energy, that's less heat. And then we say that the sunlight feels less intense or less hot. And the way we're going to quantify that idea is with something called energy flux. So energy flux sounds kind of technical, but you can see the equation is just a simple fraction, a simple ratio. And the definition is here, the amount of energy spread over an area. So a higher flux of sunlight hitting the surface of the Earth causes warmer temperatures. Okay? So if you increase the area, what happens to the flux? And the flux is this symbol right here. Does anyone know the name of that Greek letter? The what looks like a zero with a vertical line through it? Anyone know their Greek alphabet? If if we had if it's like a 4-year school, we had like sororities and fraternities, we know, right? It's the letter phi, and it's spelled like that. So it's like PH for the F sound. So it's phi. But knowing that, what's your answer here? Give me a thumbs up if you think the flux, the energy flux, increases when the area increases, or if it decreases when the area increases. All right. Hey, you got it to show up in the chat, Maxwell. That's cool. Oh, I gotta wonder who the people's iPhone is. That's a cool name. I saw it in the chat. But yeah, so yeah, the second option, decrease, thumbs down. You are right. It decreases. So as area increases, the flux decreases
Now,
because it's this. Go ahead.
how did you guys figure that out?
So we thought about how if you divide by a bigger number, you get a smaller number. So we thought, okay, well, if area goes up, so I'm gonna use that little area arrow to represent if area is getting bigger. Well, if I'm dividing by a bigger number, but the energy is remaining the same, okay, because we're only told the area changes. Well, that means that the answer has to go down. So, if I have like 5 joules of energy, J for joules, and I divide by an area that is 1 square meter, then I'm going to have 5 joules per square meter, and that would be my flux. But if I divide instead by 10 square meters, a bigger area, but I still have the same amount of energy, well, that's where I get a smaller value. So it's just and it's really as simple as saying that if you divide by a bigger number, then you get a smaller result. Does that make sense?
Yes, so because you're dividing, you get it's a decrease, but I guess I'm wondering like, um, if you're dividing by a bigger number, I mean, what did you say? If you're dividing by a bigger number, it decreases, but if you're dividing by a smaller number, then
It increases.
okay.
Yep. Yep. And we call that an inverse relationship or an inverse proportionality. That's a term we'll use throughout the course, and it's one that we've used a couple of times. Most recently, when we talked about Kepler's laws, we talked about or universal gravitation as well. We talked about that inverse proportionality, and that's exactly what this is. And there is the proportionality. See, flux is proportional to 1 over the area. Area goes up, flux goes down.
And how do you know? I mean, like they're words, right? So it's like, how would you know what's bigger and what's smaller? Because energy is energy and area is area. Like, there's not necessarily a number to define which one is bigger and which one isn't.
They there it's true that this formula is written with words, and that's a totally fair question. It's written in words, which is pretty typical for astronomy formulas. It's actually done that way to make it look less intimidating. But we could also write this formula just with what you might see more typically in a math class with just variables. So if I wanted to write the formula without words, it would just be E over A. where E represents energy and A represents area, and they are numbers. So they will always have a numerical value associated with them.
So you would just have to know that area, I mean, that energy is always going to be bigger than area.
Not always bigger, no. I mean, in one of the examples I gave, it was 5 joules over 10 square meters. So the actual number isn't necessarily bigger.
I
They
think what
also, yeah,
I think what she might mean is because she's like, I was thinking this at the beginning too. I was like, but we don't know the numbers. But like the question says increasing the area. So we already know that the area is going to be larger. So I think that's what's confusing her because she's not seeing numbers, but because
yeah.
the equation says the area is larger. So we automatically know here that the area, the bottom number is going to be larger.
Or it's going to be changing in the direction of becoming larger. That because that's all that matters, right? It doesn't matter that it's larger than the numerator. It just matters that it's increasing. Because notice that the word refers to a rate of change rather than just a new number.
So
So
obviously, if it would have
yeah,
said increasing the energy makes the flux, and then that would have been the opposite, right? That would have been
exactly.
okay.
Yep. Then in that case, it would have been the flux goes up,
Okay.
right? So increasing the energy makes the flux increase,
Okay.
whereas increasing the area makes the flux decrease. And yeah, and I have seen many students ask the same sort of questions that that we're hearing right now. And I know that sort of that idea, but it's just not getting sort of like what the heck this weird language of equations is all about. Um, it's and we're gonna kind of keep talking about it, keep seeing it, and hopefully it will click. And it's just this idea that we have these formulas, and we always want to think about what they look like. What's the trend of the formula, which is why the slides and me focus so much on these proportionalities, these ideas where we don't even plug in numbers. So it's best, and really, I mean, just it's sort of like the most because it's not like any of you likely are gonna go into the field of astronomy. You don't need to worry about the exact joules and metric system very often, although scientific notation is a good skill. But having like the idea of thinking about proportionalities is a a useful skill that like just directly relates to lots of aspects of life. And that's like kind of why it's so highlighted here, with the astronomy ideas.
I think that's why
But
I always try to just have visuals too. So,
yes,
and I'm trying to
yes,
picture this energy bubble, and then I'm trying to picture this area bubble, and then go from there. But yeah, the
yeah.
numbers and the equations can really get you.
And often a graph works really well with these to see like what it would look like if we plotted a bunch of values and to sort of look at the curve, like so then you imagine it's like data on a graph. So in the I'd love to just go off and quickly create the graph and show that right now, but we probably should continue on. But I'll try to find some time for that to do it, so that we can kind of see, or there's plenty of ways I could squeeze a graph into a homework problem to, sort of bring the idea. Because I feel like that's another good way to visualize it, other than just some people also visualize it with like scales. They imagine kind of like two, that this equation is about like, balancing these things out. I think about, almost like a contraption. But anyway, probably could talk about it forever and want to move on. Yep, just the variable, the E and the A. Yeah, cool. That's I know you probably said that before. I wrote it up. Just checking the chat. Okay. So here we're at. This is we won't be doing, any lab experiment, but we will be talking about these ideas. So what I want you to look at from the slide is, don't actually measure and calculate the energy flux hitting a surface at different angles, but think about this idea that if you had a flashlight and you had some hole, maybe in a piece of cardboard, and you could hold that flashlight so it faced straight down through the hole, or in this case, kind of angled so that the light from the flashlight was coming down through your cut hole in your sheet of cardboard, but not directly, right? Well, then what would happen with the light that'd be created on some surface underneath the cardboard with the square hole cut in it? Well, that's what we're going to be thinking about. That's going to be our sort of experimental setup that's going to apply to understanding sunlight on Earth. And in our case, the square hole is going to essentially represent the atmosphere and the sunlight coming in at different angles at different times of the year. And then the light that actually makes it down to the surface is the light that would be on the surface of the Earth and that we would experience, just like the dogs that were basking in the sun in the winter and the summer. Just get rid of this. Okay, so if the sunlight is perpendicular, then it looks like this. So we say it's perpendicular when the light or sunlight is coming from directly overhead. So the perpendicular is referring to the direction of the sunlight and the direction of both, the atmosphere and the surface. So we're going to see that in this case, sunlight is just going to pass right through our hole, and then I know there's not really a hole in the atmosphere. It's just a way to think about like that we're taking some like portion of the sunlight. You could think of actually the hole as kind of being the Earth, right? Because obviously the sun produces light that shoots out in all directions, and the Earth is just relatively small, right, compared to all that light that's being created by the sun and spreading out through the solar system. And so like the whole Earth is the hole, is the square hole in the cardboard. It's that's the light that's being caught by it. And and then so then it comes down and it's going to hit the surface. This is where we would feel the heat of the light would be on this large blank surface, which will become less blank in a second. But then the perpendicular is this right angle. So perpendicular, just as a quick reminder, in case if you maybe, I know I've used the word a few times, but maybe it never made sense to you or you forgot. And it's just 90 degrees. So it's just that, right? So that's perpendicular. Right? Whereas, of course, parallel is 0 degrees. Then that's when you're pointing in the same direction. But here we're perpendicular to the surface. Okay, so in this case, the light comes right through and then hits the ground directly. So this is the most energy flux you can get for based on angle. This is light coming from straight overhead will give you maximum energy flux. But you might be thinking, wait, weren't we just talking about area? Why does angle matter? Well, you'll see. Hold that thought. Okay. But this is the maximum case. The reason I kind of jumped ahead and said that is because that I think that should be a good intuition that I said many times, right? High altitude sunlight's going to feel more intense. Well, that's when the sun's directly overhead. You got to be in the tropics to experience sunlight that's actually at your zenith, right? So then you're going to have really intense sunlight, the most direct possible. And in northern summer, you're going to have, something close to that. Okay. Now let's think about when there is a steep angle. This is the counterpoint, the contrast to perpendicular. See? So now the angle is not perpendicular, but instead has become smaller. So the angle has, become smaller, but is still fairly large. So I guess steep angle won't be the full contrast. It's one step away from perpendicular. So this would be our angle. I'll call this angle theta, which is you'll see again in the printed text in a second, the typed text. This is just another Greek letter, a circle with a horizontal line through it. And in this case, our sunlight is a little bit less intense, not directly overhead. Okay, there's a little bit less energy flux. Why? Well, when the energy comes through, in this case, and then hits the ground, it spreads out. Okay, so there now is a spreading of the sunlight. Notice, see, this rectangle, and it's a true rectangle, right? It kind of in 3D, but 3D perspective, but a true rectangle is smaller in area than this like parallelogram, because now it's like stretched out. Okay. And then we can have a shallow angle. Now this is in full contrast to perpendicular. So now the angle has become even smaller. It started at 90, then it went to something smaller than 90, and now it's approaching 0, right? But it's just small. Example values could have been 90 degrees, 70 degrees at this point, and say 30 degrees for a shallow angle. Those would be good examples of steep and shallow. 70 degrees for steep, 30 for shallow. And now what happens? Well, because of that shallow angle, the energy that the sunlight carries is spread out over an even larger area. So in each case, the energy was unchanged. The energy was unchanged because that's the energy from the sun. We're always going to get the same amount of energy from the sun at our distance from the sun. So, that, and yet, it varies a tiny bit, right, between the perihelion and the aphelion, but think of it as just one value. So Earth gets a fixed amount of energy from the sun. But when you're angled differently to that amount of energy, that energy spreads out over different areas, as we just showed. Okay? Perpendicular, very little spread. Steep angle, some spread. Shallow angle, significant spreading. The area is changing. So here they are, all compared together. Smallest area in green, larger area in blue, biggest area in yellow. At all three angles, the same amount of energy is in the light. The area that the light illuminates is larger for the shallower angles. The energy flux at the surface of the table is different. It's different because the area changed. And the area went up, which means the flux had to go down. So we see that the spreading out of energy due to the angle of the light is a change in the area. And the reason the area changes is because of this formula, which I'll never ask you to calculate because it's got a sign in there and you're not going to use signs even just to plug things in. But in case it's helpful, it's included here. Right? The idea here is just that as the angle becomes smaller, sine theta becomes a smaller value. And then what's it? So then because this area, because this is the angle from the horizontal, and as the area as it becomes, let's see, because we want it's going to become a bigger value because sine passes through 0 and so it's at its maximum at 90. And then as the angle, because it's the same angle they've been using, the angle from the horizontal. So then the angles going down, sine of theta is also going down, which makes the area go up. This is the way I explained it in the other section. So theta is decreasing. I'll just spend a minute on this because again, this is kind of like an extra way of thinking about it, which might not be helpful for everybody. So this is the angle measured relative to the horizontal. As that angle goes down, as the sunlight becomes less directly overhead, again, which would be like, for winter days, okay, then we have sine of theta also going down, just kind of using this notation or just using these little arrows to represent the proportionalities. And the fact that as theta goes down, sine theta goes down would require some familiarity with what a sine theta function looks like when you graph it. If you recall, you got sine passes through 0, cosine doesn't. Cosine passes through 1, and they're the most two common trig functions we use. Obviously, tangent being the third most common. And so suffice to say that as theta goes down, so does sine theta. Therefore, the area is going to go up because this right here, this A with a subscript, is the fixed amount of area that the sunlight is passing through before it gets to Earth. So that I said, kind of like that the atmosphere, that the fact that the whole Earth, however you want to think about it, it's also in the experiment, the square in the cardboard, because that never changed, right? The hole that was cut in the cardboard was always the same size. Whereas the spread of the light on the table underneath, the surface underneath, that changed. So area refers to the light that's actually hitting the surface, as you can see, right? The line connects area to the spread out sunlight on the surface, and then A with the subscript zero, which we just say A zero, is the unchanging hole in the cardboard. So then the area is increasing as the angle is decreasing, and if the area is increasing, then the flux is decreasing. And the whole time, the energy was unchanged. It was just there along for the ride. Makes perfect sense, right?
Yes, it does.
Can
Okay.
you what sin is just one more time?
The last sentence.
No, it's what sin is. Sin with that.
Yeah. Sine. It's a trig function that relates to right angles. You might know it from like SOHCAHTOA. Sine is opposite over hypotenuse.
Okay.
And it's also when you graph it, it's this essentially like it's a what's called like a wave. So it's a wave function, and just to not spend too much time on it, but what the graph would look like would be this. So you'd have a graph like this. So sine is this function that looks like this. This would be a sine function. I won't label the axes, but this is what I mean by sine. It's this graph, if you've ever seen that in a math class. If not, you're not responsible for it. It was more a way of explaining it to people that had seen that, and that would help them understand it.
Understood.
Cool. Right. Okay. So a few more minutes for a break. Now, find that. Okay. So now this is a bit of just kind of summarizing what we've been talking about in this whole section. Okay. So visualizing the sun angle. Notice in this case, this looks a lot like the pictures we've seen so far when we talked about this concept, even from the very beginning when we first saw the dogs in Eugene, Oregon. The difference is that obviously this is a lower latitude that they've chosen to focus on. Same incoming sunlight, and this lower latitude that's been chosen is not just another random one, because Eugene, Oregon was random, right? There was no special significance to that latitude. But this one there is, and we can tell right away because the dashed line, which represents the direction of the zenith for an observer at this location on Earth, at this latitude on Earth, well, it's directly lined up with the sunlight. So this is a special case because of the fact that these two lines overlap, the green line representing the direction of the incoming sunlight and the dashed line being the direction of the zenith for the local sky. Well, that means something. What does it mean? Well, I don't want to completely give it away because I'm going to ask right now. At what latitude is the sun right at the zenith on the summer solstice? And the situation that they're describing in the sentence matches the picture. So in other words, what latitude is described by this figure, which is a summer, northern hemisphere summer solstice, right? With the axis tilted towards the light. But then what latitude is this? All right. So Maxwell, Teresa, Elizabeth, Maria, Isabel, Kylie, you all think it's number 2? Well, it turns out you're right. What's the name of that latitude?
Axial tilt.
It it's equal to the axial tilt. That yes, I mean strictly speaking, yes, but relative to the equator, it has another name. It is the axial tilt. That's it. Yeah. So spot on. But what is it? What's this white line? Well, I just showed it. The Tropic of Cancer. So the because of the tilt, that's why the tropics are defined as 23.5 degrees above the equator, and in the case of the Tropic of Capricorn, 23.5 degrees below the equator, which is this one here. I'll go back, but I wanted to show both of them. So we got Tropic of Capricorn at 23.5 degrees south and Tropic of Cancer at 23.5 degrees north. So those are the tropics. And the tropics are the special latitudes that correspond to this, to the sun being right at the zenith on the summer solstice. That's how those special latitudes are defined. That's what they mean. And specifically, at the Tropic of Cancer, the sun is at the zenith at noon on the summer June solstice. And we could confirm that with our familiar formula for finding the sun altitude at the summer solstice. Okay, for the Tropic of Capricorn, the sun is at the zenith at noon on the winter December solstice, winter/December, right? What people call summer in the southern hemisphere. So that's what the two tropics represent. And everything in between the tropics, okay? It's in our book on page 105. Thank you. That is, yeah. Anytime you want to add references to the book, don't hesitate. Love that. Okay. So, but yeah, that's what the tropics mean. Oh, I was just going to say everything in between, every latitude between the tropics also has one day out of the year where the sun is directly overhead. All right. So that's the idea. Yeah. Yeah. And it's interesting they point out at noontime because none of our previous discussions mentioned the time of day. And that's just because they wanted it to be specifically, like, hey, it's right at the zenith, and it's only right at the zenith at you know, at that particular time. That the whole, I guess the noon idea would also apply to their other cases, except sometimes it would be a wider range of times because it's taking that arc and it's kind of flattening out. First day of summer, yeah, yeah. If I know I was talking to, my 11-year-old child about this because I remember being confused by this idea myself that it seems weird that June 21st is the first day of summer because it doesn't feel like the first day of summer. It feels like almost the middle of summer, but of course that makes sense in terms of, kind of the heat because, the days have been getting longer and longer. The sunlight has been getting, more and more intense up until June 21st. That's the peak. And then it starts falling off. So that means that all of your, high energy flux, high altitude sun days are evenly distributed to either side of June 21st. So in terms of the actual warmth, it feels like June 21st is in the middle, but it's chosen as the demarcation between the seasons. So technically it's the beginning of summer. Okay, couple last special day of the year and a summary of all of our simple formulas, hopefully simple, to relate sun altitude to latitude and axial tilt. And that last special day is the equinox. And it makes sense we're talking about the equinox because if we go back to the very first figures we saw for this chapter and for this section, we saw that the two equinoxes were included with the solstices in this figure that we're seeing again right here. All right. So the angle of the sun from the zenith equals the latitude on either equinox. And the two equinoxes are the spring equinox. So this is the spring equinox right here. And then the fall equinox is the one on the backside. And I just know that because of the counterclockwise orbit and looking at where the perihelion is and where the aphelion is. That's spring and that's fall. But they behave the same. And on both of the two equinoxes, you've got this rule is going to apply. The angle of the sun just equals the latitude. So it's not like the sun is the same everywhere on Earth. It's still going to vary. What is the same at the equinox on that one special day that happens twice a year? So I guess you can say the two special days is that the length of the day is the same everywhere on Earth. It'd be kind of weird at the poles because it'd sort of be like twilight the whole day. But besides that weirdness, everywhere on Earth, there's going to be 12 hours of sunlight and 12 hours of darkness. So that's just totally universal at the equinox. But the actual altitude that the sun reaches on this particular day varies with latitude. And to highlight that, I got a question for you. At the equinox, is the energy flux of sunlight larger in Eugene or La Paz? Answer this question. Okay, I got a variety of answers. So some people are saying the same. Some people have said La Paz, and then a couple of you said it would be more sunlight in Eugene. Well, let's see. It's La Paz. And the reason is because of that statement that we saw that said, which can also be written as a formula, that the angle of sunlight from the zenith equals the latitude. So all we need is just that the altitude equals the latitude. La Paz has a smaller latitude in terms of its distance from zero. Therefore, it's going to have so it's going to have a higher altitude in terms of the sunlight. So the angle, because the angle of the sun equals the latitude. So we have, and the angle of the sunlight, they could have specified, because actually I could see why that statement threw you off now that I'm explaining it, because the angle they're referring to is the angle from the vertical, not the angle from the horizontal. So when it says here the angle of the sun, but it does say from the zenith, okay. But we've gone back and forth, and sometimes we talk about the angle measured relative to the horizon. Sometimes we talk about it measured relative to the zenith. And my best advice is you just have to, always be carefully paying attention to which is which. So anyway, so because of that, because of the angle being measured relative to the zenith, La Paz has smaller latitude. Therefore, the sunlight is higher altitude, and then larger latitude for Eugene, then lower altitude sunlight. And then from there, you just go to Flux. Yeah. Yep. So I could see why. The important thing is that it makes sense maybe now or when you review this content. Doesn't have to make sense the first time. In fact, you might remember it better if it confuses you the first pass, right? I always thought about that when I took tests because I'd be like, oh, I got something wrong. And I'm like, okay, well, I'm going to really pay attention to that, what I got wrong on that test. And then I feel like I would retain it better, say, by the final. Okay, so now let's summarize that last rule. And then I have our final summary of all the sunlight angle rules. Okay, so for equinox, this is all the solar altitudes. So for the equinox, the formula is simply that the angle above the horizon, notice here we're going back to measuring an angle relative to the horizon instead of the zenith. In that case, it's 90 minus the latitude. Okay, so this is the rule for the equinox. For the summer solstice, we use this formula right here, right? Which we saw. This is the first one we saw of our formulas. So think of it as the equinox formula is our most recent rule. It doesn't include the axial tilt, which is no coincidence because the equinox is the one day of the year where the axial tilt doesn't affect the sun's altitude. The only thing that matters is the latitude. But any other day, the axial tilt does matter. And it would be complicated to figure out the altitude at all the days in between because we'd have to take into account the complicated geometry of the circle and thinking about how that affects, what happens on the surface. But if we just consider the special cases of the summer solstice and winter solstice, we don't have to worry about that. And that's why we've focused on those special days. Okay, so then notice that this formula for the summer solstice happens in June in the northern hemisphere and December in the southern hemisphere. Finally, the winter solstice formula is obviously very similar for the summer solstice. To find the solar altitude, you take the 90 degrees minus the latitude and then minus the axial tilt. And in all cases, the angle that we're referring to, which is just as a reminder, the angle in the figure, the angle measured relative to the horizon, is always at noon. So always assume that we're talking about the sun's location at noon, which is its peak location on that day. And the last thing I will tell you is, and I mentioned this a while back, that I promised I would show you how we could do calculations for the southern hemisphere. We've kind of started to because we just saw La Paz, right? Well, when we use any of these formulas for the southern hemisphere, we have to take the absolute value of the latitude. Because if you plug in a negative latitude, because you might think, well, hey, if I'm in the southern hemisphere, those are negative latitudes. If you plug in, say negative, what was it for La Paz? Negative 16.5 for La Paz, you will not get the correct value for any of these, out of any of these equations. So every time you use latitude, you have to just plug in the absolute value of the latitude, which is not a problem in the north because it's already positive, but you just have to remember to make the southern ones positive. So every time the latitude is just the absolute value. Does that make sense? Okay. I hope it does. Let's wrap this up. Okay, so quick summary of cases. Example, equator, summer solstice. Okay, this is what the sunlight will look like on the summer solstice. At the equinox, directly overhead. So interestingly, the equator, their one day out of the year where the sunlight is directly overhead is the equinox. And so I guess you might think, oh, well, then they have it twice a year. And that would be the case if it wasn't for some of the other, like the fact that all of these are approximations. It actually turns out that it's 9 degrees north is the latitude where they have 2 days. But the reason for that is beyond the scope of the class. You don't have to worry about it, but fun fact. So, but approximately, here we have the three special days out of the year for an equatorial location. In this case, Kisumu, Kenya, which has a value of latitude that's basically equatorial, or a tenth of a degree south of the equator. If we look at a high northern latitude, like Moscow, Russia, which is at 55.75 degrees north, we've got the summer solstice the equinox and winter. See, so the sun never gets very high. And in winter, it practically hovers at the horizon all day. Okay, so there we go. That wraps up everything you need to know about why axial tilt leads to different amounts of sunlight and different, kind of heat throughout the year. And with that, let's take a break and see. Yeah, and I'll upload some slides, although we're taking our time through lecture 4. It always takes a while. But we'll see if we can actually get to 5. But regardless, I'll get it uploaded. And how about we come together as a class in order to give me time to upload everything in 7 minutes. So I'll plan on being back at 9:18. So see you all then. Okay, so continuing with chapter 4 and moving on to the second section. Did someone have a question? Talking about phases of the moon. Okay. Oh, Maria, to respond to your question, I said that because we're not going to get to chapter 5 today, and we'll not be doing the chapter 5 quiz tomorrow in class, which I said we would at the beginning of today. We will not.
Thank you. Appreciate it.
Yeah. When we'll be doing it, I will let you know tomorrow around 8 a.m.
Okay.
Okay. So looks good. Okay, so talking about phases of the moon, which is included in the same chapter with the axial tilt because of some of the same concepts relating to orientation, angle, visualization. Okay, so what we want to do initially is to cover all the phases of the moon. So I will first show this kind of simplified diagram, which shows the incoming sunlight and the moon in a number of different positions throughout its cycle. And the cycle of the moon, what we think of it as the phases of the moon, are happening because of the sunlight that we can see reflected off the moon's surface. And so a full cycle is going to be when the moon returns to the same relative position between Earth and the sun, as we can see here. So getting back to A would be a full cycle, so A to A. And one phase of the moon is already labeled in this figure, which is the new moon. Okay, so now let's include our other named phases of the moon. So these are all the phases that have particular names. And obviously there are days in between, but they would just fall into the same naming conventions with the I'll tell you which names kind of apply to a whole range of days and which only apply to a specific night, just one night. So the first phase that we want to identify is the new moon. And the new moon, it happens at the beginning of the lunar cycle. And it is when the moon is positioned between Earth and the incoming sunlight, which means between Earth and the sun. Next, in the order of the phases, because we're moving counterclockwise, just like with the orbit of Earth around the sun, is going to be the phase of the moon called the waxing crescent. Waxing means that it's growing, and the crescent refers to the small sliver that we can see illuminated. Okay, then as we continue, the next phase in the cycle is the first quarter. So when we look at the moon during the first quarter phase, we see that a quarter of its surface is visible to us, hence the name. And if we think of it as a circle, we can think of it as being kind of half illuminated, right? So it's like a semicircle. But remembering that it's a sphere, it's a quarter of its surface is illuminated. Then we continue on to the phase called the waxing gibbous. So waxing means growing, and gibbous refers to an illumination somewhere between a quarter or half of a circle and fully illuminated. So gibbous is between those two. And of course, that leads us to the full moon phase, where the entire visible surface of the moon is illuminated to us on Earth, so we can see the whole, the whole side of the moon that faces us. And then we move on to the waning gibbous. So we see it has the same name, gibbous, because that still refers to somewhere between half illuminated and fully illuminated. But waning means that it's shrinking. Of course, that takes us to the third quarter. Okay, so we went from the first quarter to the full and then the third quarter. You could also think of the quarter names as referring to a quarter of the way through the cycle. So the first quarter is 1/4 through the cycle, and the third quarter is 3/4 of the way through the lunar cycle. Then we get to our last named phase, the waning crescent, which is a crescent that is on its way to shrinking and becoming a new moon and starting everything over again. Notice that the waxing crescent and the waning crescent are visible on different sides of the moon. So if you knew what to look for, then you could identify them accordingly. But more likely, you can identify a waning crescent from a waxing crescent based on the time of day that moon phase is visible. And the times of the day are listed not for the gibbous phases or the crescents in this particular figure, but for the first quarter, the full, and the third quarter. We can see the time of the day is included. So what this time of the day is referring to is when that phase of the moon is in the sky. So the new moon is in the sky from dawn until dusk, which means that it's in the sky at the same times as the sun, which is totally logical if you look at this view of Earth, the moon, and sunlight, because we can see, right, that in this case, the moon and the sun are in the same direction. So if you look from the surface of the planet, you're looking at both the moon and the sun together. It's also why it's a new moon, because in the case of the new moon, the moon is reflecting all the light off of its surface that faces away from us. So we on Earth are not able to see any of the reflected light because none of it makes its way back to our eyes. Think that you're standing on the surface of the planet, you can't see any of the light from the new moon because all that light is bouncing away from us. Right? Light comes in, hits the surface. It's a very reflective dust that covers the moon, and then it just bounces right back into space, and we can't see it. Okay, and of course, it'd be difficult to see anyway because it's so much dimmer than even if somehow this was a full moon, it'd be hard to see it in the middle of the day in some cases, especially if it's near the sun because the sun is so much brighter. But it's but it's basically almost no illumination at all. So it's just a totally invisible moon. When we get to the first quarter and this time frame, it points out that the first quarter moon is visible from noon until midnight. So that means it rises around noon and it sets around midnight. So it's going to reach its highest altitude right at sunset, which we would approximate as 6 p.m. And you can think about kind of these general times as being the times of an equinox day. So the first quarter, visible from midday until midnight. The full moon is the exact opposite as the new moon. It rises when the sun sets, and it sets when the sun rises. So the full moon is visible all night from dusk until dawn. And finally, the third quarter is going to be visible rising at midnight, up the whole night, reaching its peak altitude right at sunrise at 6 a.m., and then setting at noon. All right. Okay. Cool, cool. Oh, yeah. So I see the questions asking about a quiz. Nope, no quiz. And Jacob salutes the answer of his question. Very good. Okay. So hopefully all that made sense. We'll repeat some of it. Let's carry it. So considering the phases of the moon from kind of a different perspective and just with a different figure here, we can look at the phases of the moon as the Earth orbits the sun, showing the sun obviously distances and sizes not to scale. But you can see that when we have the new moon right here, that's when of course when the moon is between Earth and the sun, and you can see that illuminated side of the moon facing away from us. We can see a couple other little details here. The fact that obviously Earth continues to move around the sun as the moon goes through its phases. That does matter because it means that in order for the moon to get back to the new moon phase, it actually has to complete more than a complete circle around the Earth. Because if you look carefully, a complete circle around the Earth is actually completed right here. And you can tell because look exactly where the moon is located relative to Earth. That's one complete circle. So that actually is an orbit of the moon around Earth, but it's not a return to the new moon phase. We need another about 2 days for the phases to finish. And that's accounting for this movement, the fact that Earth has continued to orbit around the sun in that period of time. Because of course it's about a twelfth of Earth's entire orbit around the sun has occurred by the time the moon has finished its orbit. There's different names for these two um, periods of the moon, but you're not going to be responsible for them, so I won't burden you with their names. But do notice that there is a slight difference between them. When we talk about the phases of the moon, we are talking about the full return to the same phase, which is this one here. So the longer of the two, which is just the complete sets showing to go from new to new. Okay. And then that band of phases shown at the bottom is the moon as seen from Earth, whereas the figure that I just drew on would be the moon, Earth, and the sun as seen from above the ecliptic plane. So if you see a gibbous moon at 5 p.m., is it waxing or waning? Think about those time frames that I told you about. If you see a gibbous moon at 5 p.m., can you say for sure, is it waxing or waning? Okay, I got one vote so far. 2 votes. 3. Okay. So many of you went with waning, a few with waxing. Let's look at the answer. It's waxing, not waning. And there's a way to tell, which is an important part of understanding the phases, and is that if you can if you can think about this aspect of why the waxing moon, the waxing gibbous, is visible at 5 p.m., but the waning gibbous is not, then you're in good shape of understanding the phases. Let me just point out this way that when we think of the full moon, well, the full moon rises at sunset. So the full moon would rise at, say, 6 p.m. and set at 6 a.m. Well, the waning gibbous has to rise later than that. Because if you look at the times of the day, right here, by the time we get to the third quarter, the rise time went from dusk until midnight, which means that the rise time of the waning gibbous is going to be between dusk and midnight. So when you have a waning gibbous that's just a little bit smaller than a full moon, it will, so say like just a day after the full moon, it's going to rise just a little later than the full moon did. And then 2 days later, the now even smaller moon, right, still noticeably large, but not full, will rise even later. So each subsequent day, the moon will rise a little bit later until you finally reach a point when you get to the third quarter phase where the moon is rising at midnight instead of approximately 6 p.m. That means that the waning gibbous is not in the sky before 6 p.m. And really, we would say that, that it's going to rise at the earliest at 6:30 or 7 p.m. So, 7 kind of being like a safe bet. So that would be your earliest possible rise time for the waning gibbous. And its visibility is going to be, in the middle of the night, or at least the early night, 8 p.m., 9 p.m. And most importantly for this question, it's never visible. The waning gibbous is never visible at 5 p.m. It's not in the sky at that time. Okay. Yep. Mixing it up with a waxing crescent. Well, hey, that's a mistake that I think you could, easily address. So it's better than it making no sense at all. You see, identified what the issue was. So yep. And then it's kind of a cool thing to be able to do with moon phases once you know these rules, because you can look at the phase of the moon and tell somebody, oh, hey, that's a waxing moon because of what time of day it is and when you see it. So like if I see a crescent moon and I see that crescent moon in the morning, then like around like 7 a.m., then I know that what I'm looking at is a waning crescent. Because I'm this is like a moon that's on its way, to becoming like a new moon. Yeah. All right. Okay. So this is just a quick way that you could consider the moon as a pumpkin and your head as the earth. So this is a something that you could do on your own with a pumpkin, or maybe if kind of the wrong time of the year for pumpkins. So maybe you could just do it with a ball or any spherical object. Go stand in a dark room or a moonless night without any street lights. Get a lamp or a flashlight, and works well in a closet. When I've demonstrated this for at-home versions of labs, I've done it in a closet myself, and got a lamp, got a ball, and you can then show the different phases, because you can see like what it what it looks like, how illumination appears. And again, your head represents the Earth. Okay, so when you do an experiment like that, you can think about a question like the one that's being asked here, which is during a new moon, what percent of the moon's entire surface, irrespective of what we see, is illuminated by the sun? During a new moon. Okay.
What does irrespective mean?
It means with like without dependence or not considering. So not considering and irrespective would be synonyms. Okay. So three seems to be a very popular answer. I think that, and that is the correct answer, and showing that you've got this concept down, many of you do. And that concept is simply that it the part of the moon's surface that's illuminated by the sun is always 50%. Okay? When we don't consider our view of the moon, the part that's illuminated never changes. And we can see that in the figure, right? If we look at the figure, there's always half the moon bathed in sunlight every time. See? Every single point of the moon's orbit around Earth, there's always half that's lit up because there's always half of the moon facing the sun, right? There's no literal dark side of the moon. There's a side that we never see because of a particular orbit of the moon, the fact that it rotates at the same rate that it orbits, so that there's always the same side facing us. So we always see the same craters. And we'll talk about that when we talk about orbits a bit more. But there is still a day-night cycle. If you were to stay at one point on the moon, the sun would rise and set. It's just that the lunar day is about 14 Earth days. I mean, I guess well, that's the time of light. The full day is a full a month, so it's about 29 Earth days for the sun to rise and set. It's a very long day. But then the counterpoint to this, what percent of the moon's surface reflects sunlight in our direction at a new, for a new moon? Well, I'll just give you the answer. It's 0%. Because as I said before, when you have that new moon phase, all of the light is bouncing off the moon back in the direction of the sun. And more importantly, for this question, away from us. So we can't see it. All right. So quick kind of thought experiment about what it means for the moon's orbit to be horizontal. And by horizontal, we mean approximately lined up with Earth's orbit around the sun. So horizontal would be the ecliptic plane, because remember the ecliptic is the name for our orbit around the sun, also the name for the sun's apparent path through the celestial sphere, because that's two ways of thinking about the same thing. But if the moon instead orbited in the vertical direction, things would be really different, right? Be really strange. We would have a very different perspective of the moon. Uh, Probably most significantly, it wouldn't rise in the east and set in the west like everything else. It would, it'd behave very differently in the local sky, you know? Um, and I guess, well, no, that's not quite right. It still would, but it wouldn't take a path that would look, like, yeah. So it's still, except for like some, just like at the pole, but at the poles you would see it all day and all night. So actually, yeah. So it'd be really strange. It sometimes really wouldn't rise and set. So I think that is basically a fair statement. Because if you think of, the Earth is spinning, I won't spend too long. This is just a weird kind of hypothetical. But if we had, the Earth is spinning this way, and in this case, the moon and the axis is like this. The moon is like in the plane of the screen, right? So instead of, the way it actually orbits, which is like this, right? Where its orbit is, kind of like 3D going behind the Earth, in front of it, and so on. Here, it's, just going directly over the North Pole sometimes, and then, crossing to the equator and directly over the South Pole. And this whole cycle, takes about a month, right? So say 29 days. And, the Earth, of course, rotates on its axis once every day. So that means that the moon essentially is motionless, for each day. And I didn't mention that before, but that's important to consider, right? That the moon's orbit is long enough that it doesn't move significantly in its orbit over the duration of a single night. It moves enough that you can measure it with like an accurate telescope or whatever, but you're not going to notice, that movement without making careful measurements. So you can think of the moon as being, just fixed in place, fixed in that one phase each night, and it only varies between nights. But in this case, with this weird lunar orbit, like if I was in the northern hemisphere, right here, I would see, at this particular point in the moon's orbit around Earth, I'd see it, and it'd be visible all day and all night. But then, sometimes it would be obscured by sunlight. And then as the sun set, then it would just suddenly become visible, but it would just be, at the same altitude. Its altitude wouldn't change over the duration of that day. It would just like hover at that same point above the horizon. And then a day later, it'd be at a different point and do the same thing, but lower, right? Until it just becomes completely invisible, right? So like an observer in the northern hemisphere wouldn't see it for half the month. So very, it's interesting that just such a relatively small change in its orbit, results in such a different perspective. Cool to think about for like a science fiction, like novel or story, right? You can just make these slight changes to a world, and then all of a sudden things behave very differently, right? And this is talking about imagining what I was just talking about. And would you still see phases? Well, think about how you would answer that. I'll leave it up to your own speculation and imagination. And this is doing it yourself, because you can simulate that weird effect of the light by using a ball and a flashlight in a dark space. Okay, so there we go. Kind of quick introduction to phases of the moon, but I think a good baseline of what I want you to understand, what you need to understand for this class. So now we're going to get to eclipses. Eclipses involve the moon. They always involve the moon. Sometimes they involve the moon blocking the sun. Sometimes they involve Earth blocking sunlight from the moon. And those are the two types of eclipses. And so we'll start by talking about the solar eclipse. And the solar eclipse occurs with which phase? The new moon. So the solar eclipse occurs when the moon is like this. So when you have a new moon, in other words, where the view from Earth is looking at the moon and the sun in the same direction. Or to put it another way, solar eclipses occur when the moon is between the sun and Earth. And what happens during a solar eclipse is the moon exactly passes in front of the sun. So we have a perfect alignment between the moon and the sun. As you know, just from like thinking about it, they obviously don't happen all the time, because it's likely you've never seen one, right? A solar eclipse. And even when they do happen, you probably remember when the two of them happened across North America in the last few years. People had to travel, unless they were lucky, to other cities to get a good view of it. And that wasn't just because of the weather or something, it wasn't just about getting away from clouds. It was because you had to be at a particular location in order to see the total solar eclipse. You could be in lots of locations and see a partial solar eclipse, but you wouldn't see what's called totality or the total. All right. But when you happen to be in just the right place at the right time, you would see the new moon block the sun. And we see the moon passing directly in between the Earth and the sun. And due to the Earth and the sun having almost exactly the same angular size, and that angular size is about half a degree, the covering that the moon does is almost perfect. So the moon just covers the sun. It doesn't cover anything other than just the sun's surface. So it's not, it's not like excessively large. And it's also not so small that it can't quite cover it. Except for occasionally that second case does happen, and that's called an annular solar eclipse or a ring of fire. And that's when the moon is just a little too small to completely cover the sun. And why does the moon change size? Because the moon's orbit is not a perfect circle, which means sometimes the moon is a little bit further from Earth. And if that happens to coincide with a new moon, well, then you've got a new moon with a smaller angular size. And that smaller angular size means that it doesn't quite cover the sun. All right?
I'm sorry, what did you say that was called? Annular?
Annular solar eclipse.
Thank you.
Yep. Annular. Annular. And if you look up Ring of Fire, that's the common name for it. So this is showing the orientation of the sun, moon, and earth that leads to a solar eclipse, which we kind of saw in a previous figure. But what this figure also shows is that shadow that the moon creates. When a shadow is cast in space, it takes a almost perfect cone shape. And this happens with shadows, normally as well, but sometimes it's not as perfect because the source of light isn't sufficiently far away. But when you have a really distant light source, you get this nice cone-shaped shadow. It's just kind of dwindling down to a point, and the shadow created by the moon gets quite small by the time it actually reaches the Earth's surface. And that means that the actual shadow cast on the surface of the Earth is only about 70 kilometers across on average. So that's why you have to be at really particular locations in order to see the total solar eclipse, because you have to be right where that shadow is on the surface. And the shadow moves across the surface, because you can imagine that this shadow started somewhere on one side of the Earth, and then it moves across as the moon orbits. And interestingly, the rate at which that shadow moves across the surface of the Earth is exactly equal to the speed of the moon relative to Earth, which is about 1 kilometer per second. So you've got this shadow that is, a circle essentially. Sometimes it gets kind of spread out because, of course, it's being cast onto not a flat surface, but a curved surface. So it's more spread out towards the edges of that curved surface. But you've got that circular shadow, and it's moving across the surface of the Earth at 1 kilometer per second. And if it's about 70 kilometers wide, then you can think that you've got somewhere between 70 seconds, which is a little bit actually on the short side, and then up to a few minutes is how long the actual total solar eclipse will last. But it will only last up to about 5 minutes. That's like your maximum time that you would be completely in the moon's shadow. To hopefully drive home that idea of that it's literally just this relatively small, sort of like county-sized shadow that's being cast on the surface of the Earth. You can see it here. I'll be right with you, Teresa. You can see it here on the surface. So this is a view of Earth during a solar eclipse, and you see that dark smudge that's kind of near the 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 furthest part of the Earth that they can see from the space station. That is literally the moon's shadow being cast, and in this case, we can see it kind of at the upper atmosphere. But of course, it goes all the way down to the surface. So everyone underneath this is in a total solar eclipse. They're experiencing one. So, Teresa, go ahead.
Is it true that it never exceeds 7 minutes?
Yeah, that's right. Yep, 7 minutes is your absolute best case.
Thank you.
Yep. Yep. Yeah, and it's got a combination of kind of, Earth's rotation combined with that speed I mentioned, and then being in the kind of towards the edges where the shadow is elongated. Yeah. Yeah. And you'll notice that when you look at like paths of solar eclipses, the times where you get those really long periods are always going to be where the first starts or first ends. So often like early in the morning, if you have to be at the location where the solar eclipse is at like 7 a.m., if it's the right time of the year, then that's like kind of your best case. Okay, so quick review of the geometry of the solar eclipse. Okay, so there's only a solar eclipse when the Earth passes through the moon's shadow. So we need this direct alignment. But as I mentioned a minute ago, it doesn't appear to happen all the time, right? Well, why is that? Okay, well, most of the time we miss it. We miss it because we're not right in that shadow. And we also miss it because the moon is a little bit below or a little bit above the Earth. Okay. Now, here it's sort of shown as a dramatic difference, but of course, all the scales are not, accurate. But the fact that the moon is shown below the Earth is accurate because the orbit of the moon is slightly tilted relative to Earth's orbit around the sun. And that means that most times when the moon is in the new moon phase, it doesn't happen to be quite right, quite lined up. Instead of being like this, it's like that. Because that's, this going to be the majority of the time because of those relative tilts. So you have to have a new moon coincide with the alignment of the sun, earth, and the moon. Okay? You have to have everything lined just up. And then they point out that even during a new moon, the moon's orbit is tilted, and it says, why? Well, because of the axial tilt of the planet itself. And the tilt of the moon's orbit around Earth is not as large as Earth's tilt. It's only 5 degrees, but it's still enough to make the solar eclipses relatively rare. Okay, so that's a solar eclipse. The lunar eclipse is the other type, and that's when the moon is in what phase? Full moon. Because a lunar eclipse is when the moon passes through Earth's shadow. So instead of us having the moon's shadow cast on Earth, now we have the moon within our shadow. So these are much more common, although they do still require alignment. The reason they're much more commonly observed is because you don't have to be in that small path and have that chance of seeing, the total solar eclipse for a few minutes, at most 7. Instead, you just need to be on a whole one side of the Earth. So you got a whole hemisphere in terms of longitude that's able to see a lunar eclipse. And the reason it's not the whole planet is because the lunar eclipse only lasts a couple of hours, so it's not enough time for everyone to see it, for the whole planet to go through night. But still, over half the planet is able to see a lunar eclipse. Right? Sometimes it's not going to be ideal because you might see it just around sunrise or just around sunset, but a good chunk is going to see it, during the middle of the night. And what will happen is you'll have a full moon. It'll appear as a bright illuminated full moon. It'll gradually dim and then become red. Okay? And why? Why does it become red? Which is the answer here. Well, does anyone know? Oh, is the lunar eclipse 1 hour to 1:40? Okay. I was guessing at 3. Makes sense. It's shorter than that. Okay. Yeah. So the lunar eclipse lasts a maximum of 1 hour, 40 minutes. That sounds right. But why red? Why is a total lunar eclipse cause the moon to become red? Anybody know or have a guess? The sun, yeah, but indirectly. The sun's involved, but that's not the main reason. Shadows, again, partially because the moon is in Earth's shadow. So you might think it would just be totally dark, right? Because we see, you know, it's the moon is in our shadow. So why is it even illuminated at all? Well, here's what it would look like. So going from just a typical full moon, which most of the time, right, would just stay that way all night, rise and set. But during the times where this full moon passes through our shadow, it begins to get covered by Earth. So we see the actual circular shadow caused by Earth that's starting to cover the moon. And as it covers it, the color doesn't change. All right, Teresa, go ahead.
So I was reading and it says that it turns red due to a phenomenon called Rayleigh scattering.
Okay.
And
Yeah.
what would that mean? I mean, I'm reading in our book and it's saying that it's Rayleigh scattering. The effect is similar to sunset appears red. I'm not understanding that. Can you explain that a little bit, please?
Yeah. It's because of the bending of the light and only the red light making its way through the atmosphere. So when we see sunrises and sunsets as red, that's because all the other colors have scattered and only the red light is making its way to our eyes. So Rayleigh scattering causes the blue light, the green light, even the orange light to get scattered because it's all the shorter wavelengths, which we'll talk more about in chapter 5 about how light varies from blue being the shortest wavelength, the red being the longest. And the fact that red is the longest wavelength light, it's the only one that doesn't scatter, it's the most difficult light to scatter, and it's the one that will make it through the most atmosphere. And I'll show you a picture. In fact, right here. So let's do one last thing. I know we just got 3 minutes. We'll wrap it up. Okay, so here we have the lunar eclipse. And it says Earth doesn't have hard edges. What the heck does that mean? It means it has an atmosphere, not shown to scale here. But if you think about the sunlight coming in, here are the colors that compose white light. Okay, and though those colors spread out, and the shorter wavelength light, all the way from violet, and this one should probably be like a blue. It's not meant to be black, and then all the way up to green and orange to red at the other end of the visible light spectrum. Well, all the shorter wavelengths bend or scatter and don't make it through the atmosphere. So only the red light makes it all the way through the atmosphere. And there's two ways to explain it. You can explain it with something called refraction, which is the bending of light. And then you can also discuss it through Rayleigh scattering. Like a lot of physical explanations, there's two ways to look at it. And the takeaway is that the red light makes it all the way through the atmosphere. And it really is the same reason that sunrises and sunsets are red, because at sunrise and sunset, our view of the sun is through a much thicker amount of atmosphere as when the sun is more directly overhead. And then, sunlight appears yellow when it's more directly overhead. But when it's low at the horizon, it appears red because all the other light doesn't make it to our eyes. In this case, we're not concerned about the light making it to our eyes, but instead making it all the way through, going back out into space, and then reflecting off the surface of the moon. So when we see the red moon during a lunar eclipse, we're seeing the reflected sunlight from all of Earth's sunrises and sunsets. So it's almost like from the perspective of the moon, the Earth would be like this dark, kind of almost like a new Earth, and it would have this like red ring around it. And that's the light that's actually then getting, if you were standing on the moon as an astronaut, you'd see the Earth, blocking the sun, and it'd be more than big enough to block the sun and completely block it, but it would have this red halo around its edges. And that's the light that would be bouncing off the surface of the moon and then getting back to Earth to be seen by people on Earth. So it appears red in the sky. Okay, so we got to wrap it up. We don't have much left, at least. So we'll briefly talk about tides and and how we measure the day at the very beginning of next lecture. I'll just do it in a couple minutes. Okay, but we'll finally be done with chapter 4 because you asked so many good questions. But it's also a difficult chapter. But we gotta call it quits for today. I'll go ahead and stop the recording.